All right, everybody. I hope you had a great week off last week. I know it's Friday. It's like I haven't seen you for 3 weeks. Um, I've graded pretty much everything except for the midterm, which you just handed in pretty much on Friday last week, and we'll try to get these that graded this weekend. Um, so for like the next half hour or so, this is not a super long lecture. We're going to talk about transactions and what they are, what they mean, what they do. And we'll follow the slides pretty close on this one. It's kind of like I'm not gonna say boring lecture, but it's a little boring. Anyway, but we'll try to pepper in a few anecdotes and facts along the way. By the end of the lecture, you should be able to define what a transaction is, explain this ACID properties, ACID properties, and figure out the different transaction modes in SQL, and kind of how these isolation levels help us manage concurrency. Anyway, so we'll we have to kind of stick to the slides for this one. It's a little bit boring, but it is what it is. So the magic of transactions really comes from this thing called the ACID properties: atomicity, consistency, isolation, and durability. And here's kind of how they work in practice. So you start a transaction literally by typing begin transaction like this. Then you execute your SQL statement, whatever it is, select star from, you know, course. And then you can, if everything's okay, you can do something called a commit. And this makes all of your changes permanent. And we'll come back to that in 1 second. And if you don't want those changes to be permanent, you can do something called rollback. So everything under this begin transaction would either get committed, or any changes that you made, we can go back to the start. And let me show you what I mean. So instead of doing select star from course, let's say we do insert into or let's say insert into course. Why is this going so slow? Enter values. We'll say, I don't know, hold on. We'll just make it up. 1, 2, 3, 4, 45 hours, 3 credits. Name, I don't know, introduction. Oops. Introduction to transactions. And then what's the French? I don't even know. Introduction a la. Um, oh, it'd be probably O. It's not a language course. O transactions. We'll close that out. Right, so this should technically insert into our course table, and then we could do select star from course, and we should be able to see this, right? But we do have our rollback, and we'll come back to it in a second. So check this out. There it is right there, right? 1, 2, 3, 4. But if I do this select statement outside of our transaction, and I just run this, you'll notice that it's not inserted, right? So this rollback allows us to insert and do anything we want, but then it's like an undo effectively. But you do have to have the begin transaction in order to have this rollback, right? Now, if we wanted this to become permanent, we would type in commit. I'm not going to do this, and then the rollback, it's not going to matter. I'm not going to do it for this demo just because we'll have to do it in class. Right? Makes sense. That's kind of a transaction. So we'll just talk about ACID just for a second. So why we need ACID? Atomicity, atomicity, yeah, atomicity prevents half completed work. So this means that, take for example, you have a huge database, and there's multiple people working on it. Billions of records, transactions, and the computers. There are delays. So this actually prevents something happening in the course of your code somewhere else on the planet or wherever, so that you guarantee that your changes work. For example, if I do this insert and there was some kind of uh, foreign key that whatever it was dependent on this primary key, and someone deleted this as I was doing this insert, it means that my insert could happen just as that deletion was happening, and it would cause an error or it could cause the whole database to be corrupt. That's why we can actually put in checks in here, and I'll show you in a minute, so that we can guarantee that this worked before committing it to the database, before committing the whole change. And then we can check it as well, right? We can, so like you saw, I did the insert, then I can actually, check to see if it worked. So that's part of preventing half finished work. Consistency, ensures the database rules, like I was saying. Isolation keeps concurrent users from looking at changes that you've done before you've committed them. It's almost like Git. It's like a very weak version. Durability, makes sure once you commit, the changes won't disappear. So that your commit is actually right, kind of where the word comes from. Anyway, the ACID principle guarantees that you can build applications without the fear of data corruption or unexpected side effects, right? You don't know what other people are doing on your database. So we can keep diving into this. When I say your transaction is atomic, I mean it's invisible. Whether it's a single update or like a batch of inserts, the database ensures either every part completes or none of it does, right? So way back before my time in the 70s, databases didn't have built-in transaction support, and developers had to write code for the rollback procedures. So if there was a partial failure, you'd have to have an actual line of code that'd be like, if this is failing, then, reset the whole database. Now modern databases kind of handle all of this stuff. We can, I guess there's a couple options: commit versus rollback. This is kind of the flow. Um, on the left side you see the commit flow: begin transaction, then your SQL statements, then commit the transaction. And on the right you can, begin transaction, say there was some error that happened in here, then we can roll back so that those changes doesn't affect the database. Imagine you're transferring $500 from an account A to an account B, and if the debit succeeds but the credit fails, this is accounting terms, you can roll back so neither account changes balance. Without the rollback, you can lose money, right? Or at least confuse everyone involved. This happens sometimes still. In programming, we call it like a race condition. So you know, so consistency. I can't even say these words sometimes. After every committed transaction, the database must still adhere to all its rules: primary keys, foreign keys, the constraints, you name it, whatever it is. So if a transaction would violate the rule, the system forces you to roll back. Consistencies ensures you never end up with, we'll call them orphan rows. So like I said before, if I did an insert into course and this number 1234 or whatever the primary key was, I don't like that these are like that, but it could cause, another table to have a course 1234 and it's not in the course table because there was some kind of inconsistency. Isolation, it's basically managing concurrency. That's all this is. So if I'm editing a customer's address in one session and you're updating the same record in another session, isolation ensures that we don't step on each other's toes. You won't see my uncommitted changes and I won't see yours, and at least until each of us commit. That way, each of us work with a clean, predictable view of the data. And finally, durability. It makes sure that once the transaction commits, nothing short of a nuclear strike will erase it. Um, under the covers of the database, they use a write ahead log. So before any data file changes, the intent is logged on the disk. So if the server crashes, it will replay the log to reapply the committed transactions. I know it's a mouthful. You'll learn more about this as you become like a DB admin if you want to. And then so it's like a history. So it'll there's so much happening in these databases when you actually click this execute button, right? So it'll save, even though you're not saving this as a file, it will save these transactions, run them. If the whole database crashes, say halfway through, or the computer crashes, it can go back and try to fix it. That's like, when your computer crashes and it says like Windows is trying to fix your whatever and it never works half the time, but that's what that's doing in the background. All right, so SQL Server, in particular Microsoft SQL Server, they give us three ways to manage the transactions. You've seen them: begin transaction, commit, or rollback. We can do those yourself. Then those are called explicit transactions. So we tell it what to do. The other way is we can enable something called implicit transactions. And this will basically say SQL will start a transaction for you with your first statement. It still requires you to commit a rollback, but you don't have to specifically say begin transaction at the start. So you can do this by typing in set implicit transactions to on, and then basically everything becomes a transaction. Why they don't do this all the time, I have no idea. Probably a resource option. For sure that making transactions like this are more costly on the CPU than not doing it. But the trade-off is, you can't roll back. So with explicit transactions, so that's the one where we begin transaction at the top, we can manually bracket the work. And when I say bracket, it's basically anything in between these. But I can actually do, oops, sorry, I can actually do end transaction as well. So I can make multiple, oops. And sorry, it's not called end, it's called commit transaction itself. So wouldn't need this. But we can actually group these together. So for example, let's say I want to, I don't know, we'll have two of these, right? So we'll have this one here and this one here. But let's say I don't want this select statement to be in a transaction, so we can kind of group this stuff together. It kind of looks like this. Oops. Let me scroll. I have a window. It's in a window. So right, so we can do something like this, and it kind of groups everything together. Would you do that? Not so often, but it lets us update kind of three things in once or multiple ones at one time and have groups of code together. But you can see how kind of messy it gets. I don't particularly like doing it that way, but I usually just kind of use it one per SQL file. But again, that's just me. You could tab this stuff in if you wanted to, so that it would look a little bit better, right? You could do something like this, so then now at least you can see. And then that's when you bring in comments like this is insert into whatever, right? It's ideal when you need precise control, say just updating three tables, and then it blocks other users from changing your data. So those are explicit. Now we can check out implicit. Let's turn it on. So we'll do it right at the top. And I think this sets it globally. I would have to go look. Maybe one of you guys can go check. But basically, um, if I execute this, it's gonna turn it on. And now I don't need this begin transaction, but I still need the commit to make this happen. Otherwise, it won't. And I can do a rollback now. Oops. Come on. Get out of here. Right, so I can prove this. So we'll run this code and you can see there's our insert and then there it is. It's not there, right? So a little bit easier because you don't have to do a begin transaction and then commit to make it happen. But you can still do the rollback. And then the last thing is what we've been using so far. If we turn this to off and you don't have anything, these are always auto commit. So they're explicit transactions that are being auto committed because implicit transactions are off. I know it's a mouthful. In fact, unless you're a DB admin, you probably aren't going to talk too much about it. But effectively, the difference with this is every statement is wrapped in its own transaction. So that means each commit writes to the log on the system, which can like slow down your entire system if you're inserting thousands and thousands of rows, right? So you do want to pick one, unless we've been so far doing it like this. But in the future, if you're working at a company, you want to use actual transactions. And like I said, this slide is just like, hey, under heavy load, millions of small commits can actually have a huge bottleneck on the system. So there are examples in here, but I'm going to show you my own, basically how to do this because I was kind of doing this as we go. So check this out. I wrote this one to show you, and I'll just zoom it out a little bit. Hopefully you can see this. I know it's kind of sketchy. Here we go. Zoom a bit. There we go. Okay, so um, SQL has tries and catches, just like C Sharp, Java, JavaScript, Node, whatever, Python. And it starts like this: begin try and then end try, and then it has obviously a catch where it says begin catch. And this is where this comes in useful. So here's an example. We're going to begin the transaction, and then I'm going to insert into the course. And this one, this succeeds. So if I was running this without the begin transaction, this would work no problem. And then this second insert, it fails because we already have a new 100 primary key in the course. This is actually why I don't like. Um, they should have auto generated primary keys in this, but we'll this is good for an example. Anyway, so this would fail. If we get down to here, it means both of these worked. But just like a try and catch in programming, they didn't work. But we inserted into the database. So if we didn't have a rollback, then this insert happened, and then we wouldn't really know what the heck is what happened, right? It would just say transaction committed. But in this case, if something happened, if something went wrong, and we'll come back to this active state in a second, then we're going to roll back the transaction. Then we'll just say there's an error message. Everything hasn't been committed. So this is a prime example of something simple that you're trying to do. The unfortunate thing is like we do have to write all of this code for simple to inserts, which seems like so much work, but that's why database admins get paid so much because you have to do all of this work. Um, for MSSQL, the syntax is not the same on like MySQL and Postgres. X act state is a built-in SQL function that gives you the state in which transactions are in. So again, you'll have to kind of research it more, but basically, if XX, we'll call it active state. If active state is 1, then there's an active user transaction, and it means then we can commit or roll back if we want to. 0 means there's no active user transaction at all, and then -1 means that it's uncommittable. So this is kind of like the exceptions in your tries and catches, and basically it says all we're saying is that if it's not 0, then we want to roll back. The other two conditions are 1 or -1, which are both bad. So we want to, that's why we're checking this. You could technically do this, but this would just we're not. You might have a scenario where you don't want to roll back active uncommitted transactions. Again, mouthful, but it's kind of advanced. We'll come back to it later in this at the last part of the semester. But Long story short, this is how you do it. This is how you check it. So if you're following along in the side slides, basically 23, 24, and 25, they show all four variants and the different orders, right? Read, modify, write, and the steps leading to lost updates. But the bottom line, if T1 and T2 both base their updates on a stale data, one of the changes get lost. Higher isolation levels or optimistic conflict detection, again a mouthful, are how we kind of avoid this. So we can like group things together effectively. I told you this lecture is it's a little chatty as opposed to the samples that we usually do. So there's this thing called what would you say? Non-repeatable reads. So non-repeatable reads means when transaction one reads a row and transaction two updates and commits it, then transaction one reads it again. It's seeing a new value. So if your logic expects stable data within a transaction, it can break your assumptions, meaning it could break your if statements, it could break how your transactions work, and ends up in things like this phantom reads. So phantom reads involves if transaction one queries for all orders today and transaction two inserts a new order and commits it, then transaction one requeries, suddenly there's a phantom row, right? So this can screw up things like aggregates or like paging. So if you're on Facebook and you scroll to the bottom and you see that, well, it's not Facebook anymore, but it used to do this. So there'd be like page one, page two, page three, four, five, six. Reddit does this, and they have 4chan. So you can scroll to the bottom, and if you click page two, in fact, 4chan does this explicitly, which is annoying. If you go to page two, you actually it's not ordered. You can actually see stuff on page two that was on page one. So these are phantom reads. Very big problem on like large websites like Reddit, 4chan. They could totally avoid it, but I think they just don't. So yeah, I know it's advanced now, and the times that I've used this stuff is very minimal. But if you are planning to go in to be a database administrator, this is the stuff you would deal with daily. As like a full stack developer, you probably not use this as much, but a DB admin would eventually go in and yell at you or fix it. I mean, you should do. Don't listen to me on this. You should be doing transactions and stuff, but there are we've been talking about isolation levels, so there are five in SQL Server in MS SQL, and I'm pretty sure in MySQL too. It's been a while, but there's read uncommitted, read committed, repeatable read, snapshot, and serializable, and each of them prevent a different set of anomalies. So your job is to pick the isolation level that meets your criteria to maximize the amount of memory versus processor speed versus how much CPU is being used. But we'll just explain a couple of these for a second. So read uncommitted lets you see dirty data. That means dirty data means there's no shared locking mechanism. It has maximum concurrency, but the lowest data integrity. Only use it when you don't care about absolute accuracy, like when you're ad hoc reporting in, I don't know, a data warehouse. If you're writing a quick website, there's going to be four people on it in a year. Sure, you can use this, but it's not great. That's why they call it dirty data. Just like nuclear wastewater is called dirty water. Similar, right? The default's called read committed and read uncommitted. They call it it's for ad hoc because it's fast. It's super super fast. You can't get it faster because there's no logging, there's no nothing. You just get what you get. The default is read committed, and this prevents dirty reads by basically checking on shared locks on the data and then releasing them. So you can still get non-repeatable reads at phantoms, but it's next level above uncommitted. So read committed is is by default set. Again, if you're doing like mass amount of data or you're in a warehouse of data, you could do read uncommitted just for making it fast, but you can't rely on that data. You wouldn't want to put it in a report. Repeatable read. How do I explain this? Let's see. Actually, scroll down. Where did I go? Repeatable read. So this holds share locks on all read rows until the transaction ends. This prevents dirty data and non-repeatable reads, but you can still get phantoms. Yeah, it's so crazy, and like you'll run into this if you work at Amazon or Reddit or these companies where they have these massive databases or Wall Street. Um, Very rarely have I ran into it. Again, you'd be in a large company. Um, snapshot isolation. This basically says every transaction is read only, and there's no locks for the reads, and writes only fail if there's like a true conflict, like I showed you in the example. And then serializable is the last one. And I'm not gonna again, I won't ask you on a test in the class because you'd have to look these up anyway. I had to look these up, so you know. But serializable is like the strictest level. Can't No dirty reads, no repeatable reads, no phantoms, no updates. It puts locks on everything, so it guarantees full serializability. That's a word. Now you've been here. This is the end of the slides, but I've been saying locks a lot. So imagine two of us were working on the same database on two different computers, and I decided to start working with the course table by doing an insert into course table. And at the exact same time, or like 1 millisecond, 1 microsecond later, you click the execute button just as I click it. Well, when my transaction runs, it if you use serializable or even repeatable read, the entire database locks until this insert is done. And in the transaction, the entire database will lock until the commit is done. So this means that your transaction would fail and mine would go through. And it would be vice versa. If your transaction was happening, mine would fail. Now, this is only good in scenarios like you're the administrator, right? You don't want to have transactions fail because the database is locked, because a user is buying a new widget, right? Because you'd have lots of inserts. So there's a scenario where you don't want to set it to serializable because I don't want to lock the database so that people can't buy the same thing at the same time. Now, maybe you do in the scenario that you only have one item left in your inventory and both people buy that item at the exact same time. That could cause a problem, right? So I think there's like, if say there's a really popular, I don't know, what are people, Pokemon card or something, I don't know, whatever comes out, and you're both, someone's on a website in the US and you're in a website in Canada and you're both trying to buy the one last one, and you both click go at the same time, that would be a problem if you both got the item because the database wouldn't lock, right? So there'd be these fractions of seconds that you could both buy it at the same time, even though there's only one. So the database lock serializable in that case, you'd want to do whoever got it first would get it, and then the other person wouldn't get it. Anyway, that was a lot. I know it's like a lot of new words. I won't test you on these. I'm going to test you on the actual transactions. That'll be the next test for this. We'll do it. Actually, should we do it this week? I guess it's Friday. Yeah, we'll do a test and then because we you still have like a while to go, but I won't test you on the actual verbiage. You could just look that up. Um, let's see. So that's basically it. So we defined what transactions are, seen how to start, commit, and rollback, explored these ACID properties that keeps your data consistent, compared explicit, implicit, and auto commit transactions in SQL Server. And there are transactions in other SQLs, but they might have different syntax, but at least now you know. We looked at the tries and catches, and then we talked a little bit about concurrency control, and we saw the anomalies and how the 5 isolation levels prevent them. So when you design your next app, remember, pick the simplest transaction mode that gives you the control you need, but choose the lightest isolation level, right? That prevents anomalies because you're balancing performance and consistency, right? So at some point you're not going to want to put every insert into a transaction. Like it's just not feasible. So there's like a simple balance. Anyhow, that's it. Questions, let me know, and we'll see ya.